Hello dear student. In today's video lecture we will continue about different types of superconductors. In last two video lectures we talked about what are superconductivity, what are chemical critical temperature, and what is the Meissner's effect. That topic we had already discussed in previous two video lectures. In today's video lectures we will talk on different types of superconductor. There are basically three types of superconductors or superconducting materials. As I said, those materials or those substance which helps to carry a current at very low temperature, which is near to absolute zero temperature, that particular temperature, if any material shows conducting behavior, extraordinary conducting behavior, then that particular materials are called as superconductors. So we have three types of superconductors. One is called as conventional superconductor, second one is a fullerene and alkali metal fluoride as a superconductor, and third one is high temperature superconductors. So we will see first conventional superconductor. In conventional superconductor, or this type of superconductor can be very easily identified from the remaining two type of superconductor. So what are that actually? What is the basic thing to identify the conventional superconductors? Those superconductor which require liquid helium for cooling are called as conventional superconductor. Again I will repeat, those superconductor which required liquid helium for cooling are called conventional superconductors. In this type of superconductor, superconductivity occurs in large number of elements and their compounds. There are many examples where we can observe this class of superconductors. Among the elements, niobium displays highest critical temperature of 9.4 Kelvin in periodic table. Hence, large number of compounds of an alloy of niobium have shown such a type of superconducting ability. So, a large number of compounds and its alloy have been studied with higher critical temperature. Some of the compounds are listed below. Some of the compounds of niobiums are listed below with their critical temperature. So first one is niobium ion Nb3Sn, critical temperature 18.3. Niobium germanium, critical temperature 23.2. Niobium aluminum, critical temperature 17.5. Niobium nitride, critical temperature 16. Niobium alloys are brittle and cannot be fabricated in the form of wires. So for vanadium gallium, critical temperature 16.5 Kelvin, and niobium aluminum have been manufactured in sufficient quantity to use as a coil. However, preparation of conventional superconductors are difficult and their mechanical properties are so poor, so it is very difficult to use in a commercial manner. That's why it is called as a conventional superconductors. Now next class is called as a second class of superconductors named as fullerenes and alkali metal fluorides. It is represented as A3C60. You know, fullerene having C60, that is 60 carbons. Fullerene is having in a 12 standard, there is one fullerene, or we can say fullerene is one of the allotropes of carbon, which is a bulky or giant molecule which consists of 60 carbon, which and having hexagon as well as pentagonal rings, very particular fashion, and it looks like a football or buckyball. So this fullerene, as we know that fullerene is an aromatic compound like benzene, and that's why it shows very similar reactions with benzene, or like similar reactions with benzene. So when alkali metal reacts with fullerene, it forms alkali metal fullerides, right? So fullerenes and alkali metal fullerides can be used as a superconducting material in today's day. Recently in 1985, allotropes of carbon is Buckminster fullerene, named for the designer of the geodesic dome. Unlike diamond and graphite, those molecules go on and on, whose molecule goes on. The fullerene has a definite formula C60. Here the fuse ring aromatic system bends around with closures to form a saucer ball. So it looks like a football or a saucer ball shape molecule or a buckyball. It consists of 26 member ring and 12 5-membered rings. So it has been called as the most symmetrical possible molecule. If you look that structure in 3-dimensionally, then you can see that it is the most symmetrical possible molecule. Other fullerenes have been discovered which consist of C70 as a elongated like a rugby ball. So Richard E. Smalley Bucky, Rice University, who first reported C90 particles, predicts that Russian doll molecule can be made of C90 molecule. Look at this. Firstly, we have C60, then C70, then C90. That much number of atoms of carbon gathered together and form a very big molecule, with having a C60 molecule having trapped inside a very large fullerenes. So that you have to remember. So in diagram you can see that a 660 Buckminster fullerene molecule which having 6-member as well as 5-member rings. So fullerenes have created a great excitement in the field of organic chemistry in the world. There is a room inside the hollow balls. So inside that fullerene molecule there is a big cavity is there, or big hollow space is there, and in that space some metals ions can hold or can captured. The outer surface can be modified by chemical reactions, by doing a chemical, because outer surface is made up of what? Carbon. Because in outer surface there is some 6-member ring, there are some 5-member rings, and therefore many chemical reactions like alkene, alkyne, such reactions can be also shown on the outer surface of the fullerene. Still, no one knows what to expect from this strange new molecule. By 1991, only 6 years after the discovery of this compounds of fullerene have reported a remarkable property as a superconductor. Look at it. Recently, just 20 years back, now in 30 years back, near about, fullerene reported as a superconductors. They believe that to offer the prospect of resistance-free conductivity of electricity, not at very low temperatures so far required, but at room temperature. That means it is not possible to carry this material as a superconductor at absolute 0 temperature, but at room temperature we can see this molecule shows a very fantastic property as a superconductor. It is fascinating to construct the model of C60. As I said, it is an aromatic compound like benzene ring, sp2 hybridized carbon. The 5-member rings are introduced, the structure covers in one hands. Eventually the ball closes. Seemingly, but it won't win, some angle strain is introduced. But apparently this is compensated for, in part at least, by the formation of additional bonds and the delocalization of electron over the marvelously symmetrical molecule. As I said, there is a alternate, or there may be a conjugated type of systems which we saw on fullerenes, and that's why it show a very marvelous behavior for the delocalization of electrons. After the discovery of fullerenes, a number of compounds of fullerenes or alkali metal fluorides are reported, and this compound shows a very marvelous properties of superconductivity. In C60 molecules packed in FCC structures with a lattice constant 14.2 Armstrong, the radius of the molecule is 3.54 Armstrong. This leaves large vacancies enough to accommodate dopant of the small radii. This prompted scientists to attempt doping of thin film of C60 and C70 with alkali metals. Doping with potassium gave maximum conductivity of 450 per ohm meter. Starting with x is equal to 0, the conductivity of KXC60 rises exponentially as x increases up to the value of 3, that is K3C60. So that you have to remember. So here in alkali metal fluorides, one thing I want to highlight is that for higher values of x, conductivity decreases. But both bulk and thin samples of potassium fluorides show the onset of conductivity below 18 Kelvin with critical temperature of about 30 Kelvin. A high value of critical temperatures 45 Kelvin has been reported for rubidium, titanium fluorides. So that is one of the very important compounds of alkali metal fluorides which act as a superconductors. Now third class of superconductor is a high temperature superconductor. Again in high temperature superconductor, here there are two types. One is called as superconductor whose critical temperature is below 77 Kelvin, known as low temperature superconductor, LTS, and the superconductor whose critical temperature is above 77 Kelvin, known as the high temperature superconductors. Okay, again high temperature superconductors are classified into two types: low temperature superconductors and high temperature superconductors, depending upon the where that particular material fall on the critical temperature. If it is below 77, then it is a low temperature superconductor, and if it is above 77 Kelvin, then it is called as a high temperature superconductor. In 1986, Bednorz and Muller developed a ceramic material of lanthanum, barium, copper, oxygen having transition temperature 34. Look at this, 4 elements combined: lanthanum, barium, copper and oxygen having transition temperature 34 Kelvin, which was a Nobel Prize winning discovery, that is Bednorz and Muller in 1986. In 1988, a compound of formula YBa2Cu3O728 was obtained by heating compacted powder mixtures of Y2O3, BaCO3 and CuO at 1173 to 1373 Kelvin. This showed superconductivity at 90 Kelvin. Very nice. So many compounds of people have developed today to study the property of superconductors. Another similar compounds, that is thallium, Tl2, Ba2Ca N-1, CuN O2N plus 4. This is again one of the molecular formula whose critical temperature varying with 90 Kelvin to 120 Kelvin, and again it shows the superconducting property. One more compound, boron 1.7, Pb 0.2, Sb 0.1, strontium 2, Cu 2.8, oxygen Y has critical temperature 164 Kelvin. Thus, there is a great achievement in the preparation of superconducting material which exhibit a superconductivity at high temperature up to 160 Kelvin. The boiling point of liquid helium is 4 Kelvin, which is expensive to attain. Liquid hydrogen 23 Kelvin is hazardous, and liquid nitrogen is 77 Kelvin. Therefore, preparation of superconducting material above 77 Kelvin is easier and cheaper. Hence, in today's discovery, materials which will show superconductivity at higher temperature will continue and having the great demands. Okay, so these are the three important types that you have to remember for the superconducting behavior. Now let me come to the point that is last point of this topic, that is the application of superconductor. today with these three different types of superconductors, we have huge demand in today's era. Alloys of niobium, tin, niobium, germanium, niobium, aluminum, vanadium, silicon shows superconductivity with varying critical temperature values of 20 Kelvin. Niobium, tin, and niobium gallium always have the critical temperature values 22 Kelvin to 24 Kelvin respectively. So these alloys are very useful for which act as a powerful electromagnet. So it looks like an electromagnet today. And these electromagnets have a variety of uses, like they are used in atom smasher for high energy particle physics research. They are used in nuclear fusion research to make powerful magnetic fields, such as magnetic bottle for plasma. That means in physics it has huge demand. Then they are used in chemical laboratories for nuclear magnetic resonance machines. They are used to produce extremely high magnetic field of about 19 torr. That is a superconducting quantum interference devices called as SQUID are used to detect tiny variation in magnetic flux density 10 raised to power minus 5 torr. They can also be used in electronics to make ultra low noise amplifiers. The race to discover superconductors which work at higher temperature continues. So discovery is still going on to find something new, something better, something more beneficial to human society. Since its technical application have great financial benefits, therefore their potential uses are power transmission using superconductor, low loss transmission of DC through resistance-less cable from electricity generating power station rather than AC through normal wire in economically attractive use in computer. One of the major difficulty in miniaturization of computer chips to get rid of unwanted heat. If superconductor were used, the heat problems would be reduced. Another important application, that is powerful electromagnet using superconducting windings, are already used. It would be much easier to do this at higher temperature. So in Japan today, a prototype of train which float on magnetic field has been built up by using superconducting phenomena. So these are the some most widely used application about superconducting materials today. Still more application will becomes in future, because this is one of the very demanding research in today's era. Okay, so here we finish this topic. Tomorrow we'll see and in next video lecture we'll see the question of this particular topic. Okay, bye.